Hello, welcome again to the lecture series on engineering thermodynamics. Now we will discuss entropy. In this session, we will prove Clausius inequality, calculate entropy of an irreversible process, calculate last work during a process, explain principle of increase of entropy, and explain entropy and disorder. First, let us prove Clausius inequality. Here, I have just considered a cycle, thermodynamic cycle. AB, BC, CD, DA. These are reversible cycle. All are reversible processes. Again, AB, BC, CD, DA. This is an irreversible process. This is an irreversible cycle. Okay. You know that irreversible process cannot be represented by the solid line like that because it will not have thermodynamic equilibrium states. Now let us take this reversible process A to B. Out of that part of the process I will consider. That is also a process. This is reversible process. This reversible process, as I mentioned earlier, can be replaced by one reversible isothermal and two reversible adiabatics. Okay, this I have replaced. Similarly, take this part of the process. Do the same. Two reversible adiabatics, one reversible isothermal. This part, and so on. I go on doing like this. Now, let us look at this part only, this cycle. This is a reversible isothermal, reversible adiabatic. This is also an isothermal process because the temperature is kept constant. This is adiabatic. This is a Carnot cycle. So, this is a reversible cycle. If you consider this is not a reversible cycle. It's an irreversible cycle. Let us look at. Okay. Now you know very well for a reversible cycle, the efficiency can be defined like this. Eta is equal to 1 minus delta Q2 by delta Q. So any other cycle also I have defined the efficiency. But in Carnot's corollary, I have told, we have discussed that no engine can be more efficient than a reversible engine, that is Carnot engine, working between the same two temperature reservoirs. So now you consider this engine, any engine, its efficiency. If at all this engine is a reversible engine working between the same two temperature reservoirs, its efficiency must be equal to reversible, then E equal to sin 4 square. If any other engine means an irreversible engine, it should be less than this. That is how the sign is brought in there. So let me cut this off, cut this off. This efficiency has to be small, means this must be a larger value than this. So if I remove these minus signs, I should reverse this direction. Correct? Okay. Now, this is a x1 value. This another one is x2 value. 1 by x1 is definitely smaller than 1 by x2. Correct? Because x1 is larger. Right. That's why it is again written as, when I inverse it, delta q by delta q2 is less than or equal to delta q by delta q2 reversible. This thing I can replace by temperature relationship. Okay, you know absolute thermodynamic temperature scale, from that you can replace this value. So now I'll put this here, so I'll get this. Correct. So delta cube by T, I'll bring it here, delta Q2 I'll push it here, you will get this. Then again I bring it to the left hand side, it will become minus, but delta Q2 is heat lost from a system, so minus of minus, it will become plus. So I'll get this. This is for one process, this is for another process. Complete cycle means I'll put cyclic integral less than or equal to 0. This I call it as Clausius inequality. This delta q by T, cyclic integral of delta q by T equal to 0 holds good for reversible process. Cyclic integral of delta q by T less than 0 holds good for irreversible cycle. Greater than 0, such a cycle is impossible and it violates second law of thermodynamics. Okay, this is the Clausius inequality. Please, it's better to remember this. Now let us say entropy change in an irreversible process. So ds entropy equal to delta q by T for a process 1 to 2, correct? This must be a reversible process. Now, next thing is, you see here, less than or equal to 0 for a process. For a process, delta q by T is less than or equal to ds is written. Equal to 0 if I write, then it is reversible. Less than, so or you can say ds is greater than delta q by T. This holds good for irreversible process. Irreversible process. So consider the cycle shown in figure A and B a reversible process and C is an irreversible process. For the reversible cycle consisting of A and B, see here reversible delta q by T. I think okay. Cycle shown in figure A and B. Let us say A, B. So consider cycles shown in figure A and B are reversible processes. A and B are reversible processes. And C is an irreversible process. For the reversible cycle consisting of A and B, you know, cyclic integral of delta q by T must be equal to 0. So that means delta 1A to 2 delta q by T, then 2B to, this is 1, this is 2. So 1A to 2 delta q by T and 2B to 1 delta q by T, that is equal to 0. So from here, this 1a to 2 delta q by t can be written as minus 2b1 delta. Okay, that's fine. For the other one, considering a and c, this must be equal to less than 0. So what is that I can do now? This 1a to 2 delta q by t is nothing but this value. I have substituted that. Divide through the minus sign, or you can say this can be written as greater than this. If I bring it this side, this will become greater than this. Okay, so you can say 2b to 1 delta q by t is greater than 2c to 1 delta q by t. So this is nothing but ds, because it is reversible process. So you can write ds is greater than delta q by t for an irreversible process. Right, sir? So please note that ds, sorry, sorry. Okay, ds is equal to cycle process 1 to 2 delta q by t, provided this process is reversible. ds is greater than 1 to 2 delta q by t for irreversible. Means this is equal to how much? Reversible plus something. Okay, so for irreversible process, entropy increases. Okay, right, this is a very important relationship. Last work. Okay, let us consider a closed system. Let me draw PV. This is the process 1, 2. That is a reversible process. So delta QR is equal to DUR plus integral. It is a PDV work. It is nothing but this area. Okay, PDV work. For irreversible process, I have written the equation here: I and delta W. I cannot write here PDV because this is an irreversible process. So probably, if I say pointer in color, if I take the process may be like this. So that area may be like this. Okay, right. Please remember, right? So I delta W, I cannot just calculate using the equation PDV. Okay, these properties are equal because it all depends on the end state. This one, if you subtract, this can cancel each other. So dqr minus pdv minus dqi minus delta w I can write. Correct? Let us divide, bring this pdv here. Correct? So delta divide throughout by t. Delta q by t or delta q by t I plus pdv minus delta w by t, you will get. This is nothing but ds, change in entropy. So this is irreversible process. Okay, so let me call it as dis, des. This I call it as dis. This is the increase in entropy due to heat transfer. This is the increase in entropy due to internal disorders like friction and other kinds of things like that. So total entropy changes. This is due to heat transfer. This is due to internal abnormalities, that is friction and other kinds of things like that. Now PDV work, you can very clearly see that this is the red colored one, PDV work, and delta W work means this blue color one. So then what happens? This much work is lost. So when the system executes an expansion process, say this much area, if you look at, calculate, this much work is lost. This I call it as lost work. So the difference PDV minus delta indicates the work that is lost due to irreversibility and is called a lost work, which approaches zero as the process approaches reversibility as a limit. Thus the entropy of a closed system increases due to heat addition, that is one, and internal dissipation is this one. Okay, so this is how we can calculate the entropy. In other words, physically how to understand is this one. If you consider piston cylinder arrangement, if it is a reversible process, all the, assume this is the matter, assume matter is the gas, and all the molecules will be acting in an orderly way, and this pressure is P, correct? So then it moves, then PDV is the work done. When you supply heat, temperature increases, then the molecules disorder will start. The pressure that is acting is P dash now. P dash is smaller than P. That's why the work done will be small, and so much work will be lost. So as I said, as the entropy increases, work is lost. Correct? Work decreases. So if the process is reversible, maximum work can be obtained. If the process is irreversible, whatever work you obtain, that you can call it as actual work. Please remember that also DES, DIS meaning. So you consider again this piston cylinder arrangement. Say this is the system. With the system, you are transferring heat with a finite temperature difference, delta Q, and by T. This is this value, DES. Here again there will be friction, there will be disorder, correct, internal dissipative effect, and because of that again entropy increases. That is internal entropy, this one. Okay, so thus the entropy of a closed system increases due to heat addition, this one, and also internal dissipation. I hope you understood the concept of lost work. This is an ideal process. You can find area under the curve. This is the actual process. And this is the area that is work lost, this much. Please understand this. These are very, very important when you start studying energy conversion systems. Okay. So, in general, we can write ds greater than or equal to delta q by t equal to sine force good when this is reversible, greater than sine force good when it is irreversible. Okay. If the system is isolated, this value is 0. So delta is greater than or equal to 0. Okay. In that isolated system, if it is again reversible 0, S is constant. Correct. For an irreversible process, delta isolated, you can see over here increases. Correct. For an isolated system which does not undergo any energy interaction with the surroundings, that is delta q is equal to 0, then this will become greater than or equal to 0. If it is reversible, 0, irreversible, isolated. So, system and the surroundings together, you can call it as universe. The processes are never be reversible, always irreversible. So you can consider it as a universe as an isolated system. So entropy of an isolated system increases, means entropy of the universe increases. So that's what I have written. System plus surroundings. Please remember that entropy of the universe always increases. It's isolated. If it is, because all the processes are irreversible. So you can just write the principle of increase of entropy is one of the most important laws of physical science. It's a quantitative statement of the second law of thermodynamics. Every irreversible process is accompanied by entropy increase of the universe, and this entropy increase quantifies the extent of irreversibility of the process. Higher the entropy increase of the universe, higher will be the irreversibility of the process. So, Clausius inequality, you have studied Clausius theorem, you have studied. First law and second law determine the following words. The energy of the world is constant. So, energy can neither be created nor destroyed. Entropy of the world tend towards a maximum. So, ds is greater than 0 of the universe. Entropy of an isolation always increases and becomes maximum at a state of equilibrium. What is the meaning of that? Look here. I think I have explained in the next figure. No. Okay, I'll explain this. If the pressure here is less than the pressure here, pressure greater, pressure low, then this can move. Correct. Suppose because of this is the system where there are many gas molecules. If they exert pressure in an orderly way, and if this pressure exceeds this pressure, then only this can move, because there is an imbalance. So much of disorderliness, molecules will act in all direction. At the most, the pressure on this is equal to this pressure, it will never move. Then we say this is an equilibrium state. If the entropy increases and becomes a maximum, then all these things will attain equilibrium state. Okay. So that is the meaning of that. Entropy and direction. All spontaneous processes of nature occur only in one direction. It is from a higher to a lower potential. Anything to happen, anything in life to happen, correct? There should be a gradient. So it has to fall down, there should be a gradient. Something has to flow down, there should be a gradient. All spontaneous in nature occur only in one direction, from a higher to a lower potential. So voltage will also flow. If this is at a higher voltage, this is at a lower voltage, it will flow. Water, it is higher head, lower head, then only it will flow. These are accompanied by an entropy increase of the universe. Okay. The second law indicates the direction in which a process takes place. Okay. A process always occurs in such a direction so as to cause an increase in entropy of the universe. Universe is an isolated system, and system and surroundings together we call it as universe. Work is a macroscopic concept. Work involves orderly motion of molecules. Kinetic and potential energy of the system represent orderly forms of energy. Thermal energy is due to the random motion of the molecule is completely a disordered fashion and the average velocity is zero. Orderly energy can be converted into disorderly energy, that is mechanical and electric into internal energy, but there is a limitation on conversion of disorderly energy into orderly energy. When work is dissipated into internal energy, the disorderly motion of the molecules is increased. What it means is that work, electricity, these are all orderly energies. All work can be converted into heat. Electrical energy, E, can be converted into heat. Heat, as you have seen now, the system, as you go on supplying the heat, disorderliness increases. Because of that, all heat cannot be converted into work. There is a limit. So please understand that. There is a limitation on conversion of disorderly energy into orderly energy. Okay, into order. The work is dissipated into internal energy, the disorderly motion of molecules is increased. So you can consider always work and heat, work and electrical energy, all these are high grade energies because all can be converted to heat. But you cannot convert this into this. This is what you can call it as a low grade one. Okay, entropy and disorder. An irreversible process always tend to make the system to a system of greater disorder. An isolated system always tends to a state of greater entropy. Thus, there is a close link between entropy and disorder. Entropy of system is a measure of the degree of molecular disorder existing in the system. All these I have explained already. When heat is added to a system, the disorderly motion of molecules increase and so the entropy of the system increases. The reverse occurs when heat is removed from the system. All these have been explained earlier. So, Boltzmann introduced the statistical concept to define disorder. Entropy S is equal to K log W. This W is called thermodynamic probability, which is greater the more disorder the state is. So if I put W is equal to 1, log 1 is 0, then S is equal to 0, represents the greatest order. And this occurs only when T is equal to 0K. That is very difficult anyway. So if W increases, then S increases. Yes, this thermodynamic probability to understand, you must understand the statistical thermodynamics. So let us not get into that part. Now, First and second law combined. Let us define. ds is equal to delta q by t reversible. So we can get this, correct? Okay, from entropy definition. From first law of thermodynamics applied to a closed system executing a process, we can write this. So this is a reversible, bring in here. So this will become TDS is equal to du plus PdV. Okay, if you want, you can write this as small s, small u, small v. Again, H is equal to u plus PV, you know. Differentiate dH is equal to du plus PdV plus PdP. Du plus PdV, we can bring in here TDS. Substitute here. TDS plus VDP. So TDS is equal to DH minus VDP. Okay. These are the two thermodynamic relationship we can use. This we can apply for a closed system. This we can use it for a steady flow system. Delta Q dE plus delta W. It is general. Holds good for any process, reversible or irreversible. This equation holds good for any process undergone by closed system. When this I replace by integral PdV, then it holds good only for reversible process. Correct? I cannot define for any reversible process delta W is equal to PdV. Again, this equation holds good reversible process only. Entropy definition. So TDS is equal to du plus PdV. Any process gone by a closed system, this holds good for any process. Okay, alright. Second law of thermodynamics, that's what I said. Orderliness. Suppose if there is a vehicle, if everything is orderly, you start pushing, the vehicle will move forward. If some people are moving this way, pushing this way, some people are pushing this way, then this will not move. This will become, if both the forces are equal, then some equilibrium state it will be. So entropy increases, system is moving towards equilibrium state. So earlier we used to draw pressure and velocity diagram. Now let us learn how to draw temperature and entropy. For example, before getting into this, let me tell you this. There is a cylinder, there is a piston. Okay, right. Assume this is the system part. The pressure of the system is P1. Let us say volume of the system is P1. So pressure, volume. I know P1, I know V1. Mark this. Move the piston towards right. Maybe you supply heat reversibly and get the work W. So let us say it will take this thing, state 2. During the process, heat is supplied and you have got the work. This process I have represented on PV coordinates. So you know, if I, as I mentioned earlier, if I calculate this area of the shape, so what is this? Pressure unit is Newton per meter square. Volume unit is meter cube. Then these two cancel. You get Newton meter nothing but joule, the unit of work you get. So area under this curve will give you the work done. Okay, let us look at this. I have defined entropy for a reversible process. The process is reversible, also adiabatic. Adiabatic means completely insulated. This fellow is 0. So then ds is equal to 0. That means S1 minus S2 is equal to 0. So what you can say, S1 is equal to S2, or S the entropy, the property is constant. So if a process is reversible, also adiabatic, you can call it as isoentropy process. Then you can say entropy is constant in this case. Correct? Such a process we call it as reversible adiabatic process or constant entropy process. In general, we have written this. Let us say Q reversible from initial state to final state. I written as a TDS. If it is an isothermal process, I can take out T out of the integral sign ds. Then final entropy minus initial entropy. Correct? This is for an isothermal process. So now on an entropy, look here. How I can represent color. Okay. Temperature, this is entropy diagram. Initial state is this, final state is this. So this is a constant temperature process or isothermal process. This is the initial entropy, this is the final entropy. If you take the area, temperature is Kelvin, K. Entropy is joule per Kelvin. So Kelvin, if I cancel, this is J. This gives the unit of heat. So by drawing TS diagram, we can find out heat interaction. Correct. Suppose the process is isentropic. Is the initial state, is the final state. Entropy is constant. Area under this is 0. So what is the heat interaction? 0. So now let us draw this TS diagram for Carnot cycle. You see here process 1 to 2 is reversible isotherm. 2 to 3 reversible adiabatic. 3 to 4 reversible isotherm. Here heat rejection, here heat is added. 4 to 1 again reversible adiabatic. This is on PV coordinates. How do we represent this on TS coordinates? 1 to 2 temperature is constant. 1 to 2, yeah, temperature is constant. Wrong. Let us consider this is 1, this is 2. Here temperature is constant. That is heat is separate, Q1. Correct? Then this is 2 to 3. Reversible adiabatic. Entropy is constant. 3 to 4. Again isothermal. 4 to 1. Again adiabatic. Entropy is constant. So please remember 1 to 2, 2 to 3, 3 to 4. Okay. So this is how we can represent Carnot cycle on PV coordinates and TS coordinates. So now if we take any thermodynamic cycle, I should be in a position to represent that on PV coordinates as well as TS coordinates. From here I can find work interaction. What is the total work here? Output of the system is area bounded by these four curves. What is the net heat interaction? Area bounded by these. Okay, this much heat is converted into this much work, right? So what is the total heat supplied to your system? This area, because area under the curve, I'm sorry, like this. What is the heat rejected from the system to the surroundings? This much. What is this much? Sorry. What is the net heat? This is the thing which has been converted into work. Okay. Hope you understood. This is very, very important. I think how to represent thermodynamic system and processes on pressure, volume coordinates, and temperature entropy coordinates. And once you understand this, then studying the performance of energy conversion systems become very, very simple. So there is high grade and low grade energy I'm talking about now. The sources of energy like high grade and low grade. Already I told you electrical energy, work, here all can be converted into low grade energy. But heat, all heat cannot be converted into high grade energy. So this is not possible. So this is very clear now. So thus high grade energy, mechanical, electrical energy, water power, wind power, kinetic energy of a jet, tidal power, all you can call them as high grade energies. Low grade energy is heat, thermal energy, heat derived from nuclear fission or fusion, heat derived from combustion of fossil fuels are called low grade energy systems. So from these discussions, hope you must have understood Clausius inequality, how to calculate entropy for a reversible process, how to calculate entropy for an irreversible process which will have two parts, entropy increase due to heat transfer and entropy increase due to internal irreversibilities. And you must have understood the concept of last work, correct? And as entropy increases, last work will increase, and entropy of universe, which is considered as an isolated system, always increases, and the relationship between entropy and disorder, that is K is equal to S ln, sorry, K. I'm sorry that Boltzmann equation, right? That is S is equal to K ln W, right? Entropy is equal to K ln W. So this from statistical thermodynamics we can obtain. This we are not discussed here. So all these concepts, and finally you must have understood how to represent the thermodynamic system and PV and TS coordinate system. Thank you.